Welcome to Earth Science Lecture. My name is Professor Diane L. Pomeroy, and in this lecture, it's morphin time. Let's learn about metamorphic rock. Unlike what's presented in Mighty Morphin Power Rangers, which you can see on this slide, you don't need to be a teenager with attitude to change under pressure. The term metamorphose means to change form. You may be familiar with it from biology, for example, with the metamorphosis phase that a caterpillar can undergo to develop into a butterfly. In a similar way, metamorphism of rocks does involve the breakdown and reforging or redevelopment of previous rock material into something new. Metamorphism is the transformation of one rock type into another. The original rock, which is referred to as a parent rock or protolith, undergoes changes in mineralogy, texture, and chemical composition when it is exposed to enough heat and pressure beneath the Earth's surface. On this slide, we have a diagram that shows a cross-section of a mountain range, and we've got in the middle, we have what looks like confetti-covered rock that's actually granite, and this granite has been compressed through the process of orogeny or mountain building, and through that compressional force, some of these granite bodies have been deformed into the metamorphic rock gneiss. We're going to learn about different types of metamorphism next. Metamorphic rocks can form from igneous, sedimentary, or even other metamorphic rocks. They are the last rock in the rock cycle, which is shown here on this slide, in this diagram. So recall that there are three rocks in the rock cycle. It begins with the development of igneous rocks, which form from cooled magma or lava. And then we have our sedimentary rocks that form from those rock bodies, whether it's igneous rock or volcanoes that have been exposed to the Earth's surface over thousands to millions of years. Those materials will break down into what we call sediments, which are then deposited in watery environments. Those sediments will then build up and develop into lithify into sedimentary rocks. And so igneous rocks and sedimentary rocks can in turn be exposed to immense heat and pressure under their surface, usually from plate tectonic forces, so from compression typically, or from tensional forces. And through these forces that exist deep in the crust, so greater heat, greater pressure, the deeper that you go under the Earth's surface, that's going to cause those rocks that exist under the Earth to be deformed into various types of metamorphic rocks. There's two main ways that metamorphic rocks can form on the Earth's surface, and those are through contact metamorphism or through regional metamorphism. When we have contact metamorphism, what occurs is that magma can force its way through the Earth's crust. Sometimes it will join into a magma chamber, it'll feed into a magma chamber and feed into a volcano, and we've seen this with the igneous rock in the volcano lectures. We can develop volcanoes in this way from these magma chambers. So this magma, as it burns through the crust, can actually chemically alter the surrounding rocks. It can cause those rocks to reheat in the process, and those crystals inside can change. So recall that Bowen's reaction series happens when we add certain amounts of temperature to minerals. If you add some temperature to minerals, they develop into different types of silicates in a sequence. So recall that with the lighter silicates that form at lower temperatures and pressures, we've got things like quartz and feldspar that form closer to the surface of the Earth. And the deeper that you go in the crust, you'll form minerals like olivine and pyroxene. These dark silicates will form usually greater depth, higher temperature and pressure conditions. So when we change a mineral, remember it's not like changing phase of water, right? So with water phases, we go from solid water, which is ice, to liquid water to gas by changing the temperature. And when we melt down rock, it's a little bit different because it's not only a physical change that's occurring, where we're going from different phase states, but we're also changing the chemistry of those minerals. And that's what's happening with contact metamorphism. Where these rocks have been burned or changed by this heat, that's when we get this development of contact metamorphism. And we can see that in this diagram. So we've got a magma chamber that's developed here, and it's feeding into this volcano on the surface. Those surrounding sedimentary rocks in this diagram have been turned into what we call metamorphic aureole, or an area where we've got contact metamorphism that completely surrounds this now solidified magma chamber after millions of years. So those metamorphic rocks formed through this process of contact metamorphism, where we have a contact point between this boundary point between the magma and the surrounding sedimentary rocks, these host rocks that have now become metamorphic rocks. So the process of recrystallization occurs with contact metamorphism, and this will develop distinct types of metamorphic rocks. In particular, there's two types of metamorphic rocks that form in this way, and those are quartzite and marble. So what can happen is, again, with contact metamorphism, you have a pool of magma that heats up those surrounding rocks, in this case, limestone, sandstone, and shale. As it heats up those rocks, it's going to change the crystal content. It's actually going to cause those crystals to regrow and develop into larger crystals in general. So they'll either regrow into a new crystal altogether, or they'll grow in size. In the case of marble and quartzite, the crystals actually outgrow the remaining other silicates or other crystals that are in those rocks. So in the case of quartz sandstone, what can happen is if you apply enough heat to it through contact metamorphism, the minerals inside the quartz minerals will actually outgrow all the other substances present in the sandstone to develop into the solid rock quartzite, again, which is a metamorphic rock. Same thing with limestone. If you've got a specimen of limestone, this particular example has fossils in it. Those fossils, again, can be completely destroyed through this process, where we've got calcite that outgrows everything else in the limestone rock, and the calcite will then solidify to make the metamorphic rock marble. So again, quartzite and marble are two metamorphic rocks that form through this process of contact metamorphism. And this process that I just described to you, where some of the crystals become larger because of increased heat and pressure, is known as recrystallization. So here's some examples of some non-foliated metamorphic rocks. Foliation refers to folds or waves, like this wavy kind of surface that you can see in later specimens I'll introduce to you. So foliation is folds. Non-foliated means that there are no folds. So these specimens indicate that they formed under contact metamorphism. And there's three of them here. We've got quartzite, hornfels, and marble. So all three of these, quartzite, hornfels, and marble, are non-foliated metamorphic rocks. They're indicators of contact metamorphism. The next type of metamorphic environment that exists is due to a process known as regional metamorphism. So a region is a larger area, and this usually develops, regional metamorphism occurs when we have tectonic forces that act on much larger rock bodies. So for example, we have convergence between two continents. The convergence between those two continents will cause immense pressure to build beneath your surface, and in the addition of that pressure, those surrounding rocks will then deform, and they will actually have folds that will develop on their surface, not just in hand sample, but on a larger scale. So regional metamorphism, we're talking about a much larger area, more pressure than heat is being applied here. That's the difference between contact and regional. Contact metamorphism, you've got heat that alters the chemistry of the rocks. Here we've got physical pressure that alters the surface of the rocks. Not necessarily the chemistry 100% of the time, but more so the pressure is going to alter that surface. It's going to make it more folded and wavy, what we call foliated in this case. The process of foliation, this entire process of compression, this compressional force that's acting on the rocks, this develops what we call differential stress. So differential stress is a phenomenon where we've got pressure only on one side of a rock body at a time. So in other words, instead of having pressure evenly distributed on all sides of the rock, If you were to do that, for example, with sedimentary rocks, like we see in this diagram, we've got undeformed strata. So those sedimentary rock layers are like a cube. And if you are to pretend it's almost like a sponge or something like that, it's squishy. So if you were to take that cube and you were to apply even amounts of pressure on all sides, enough time and pressure takes place, that cube will only just shrink in size. It's not going to change its shape per se. It's just going to become smaller. So if you were to apply pressure only on one side, what will happen is that the strata will actually begin to fold and rupture. And through this folding process, we can actually see this on larger rocks as well as in the hand samples I'm going to be showing you on the next few slides. So for example, with Rainbow Basin in California, we have synclines and anticlines. We've got these folds that exist in nature from this process of differential stress, again, mostly due to compressional force acting on those larger rock bodies over time. So in later lectures, I'll teach you more about synclines and anticlines and structural changes to the landscape. So regional metamorphism develops what we call foliated metamorphic rocks. So again, foliation refers to wavy or a kind of folded looking surface. And we have three examples here. We've got gneiss, phyllite, and schist. So gneiss, we've got what we call gneissic bands that develop on the surface of this rock. Gneissic bands are essentially like stripes that flow across the surface, if you want to think of it that way. They represent the most amount of metamorphism that a rock can undergo before it melts down into magma once more. Then we've got phyllite, which is a step between slate and schist is shown here as well. So we've got all of these represent different types of foliation patterns that we can find in our metamorphic rocks. Now, the texture of a metamorphic rock is dependent on the gradation of heat and or pressure, so especially with pressure. So what's interesting is that at different points in the crust, there's different amounts of heat and pressure that can be applied to rocks that deform the rocks at different times. And so if you've got low heat and low pressure conditions, the surface of your rock is going to look very different than what occurs under high heat and high pressure conditions. And there's actually gradations or subtle changes to the amounts of heat and pressure that can be applied depending on the different phenomena that are occurring to the surrounding rock bodies to change them. So the texture of a metamorphic rock is dependent on the presence of these folds. And as we can see in this diagram, you can actually increase the grade of metamorphism going from shale, the sedimentary rock shale, to slate, phyllite, schist, and gneiss. And in fact, all of these rocks are part of a sequence of metamorphism, this progression of metamorphism that we call metamorphic grades or gradation. So there's two types of metamorphic grades, and there's grades in between this, but for the purpose of this class, I'm not going to get into them. So there's two major categories of metamorphic grade that I need you to know, and those are low-grade metamorphism and high-grade metamorphism. Low-grade metamorphism occurs closer to the surface of the earth. So again, our example here is shale, which will metamorphose into slate. So shale metamorphoses into slate. Notice that there's not a whole lot of difference in appearance between these rocks. They're often easily confused in hand sample during identification portion of exams. So shale is a sedimentary rock, and as we know, shale forms from mud that's solidified over thousands to millions of years. When shale is exposed to a little bit of heat and a little bit of pressure, it can metamorphose into slate. So slate is a metamorphic rock. You may be familiar with slate, maybe from construction or something like that. But slate, again, is a metamorphic rock that forms under low-grade conditions, which again is low temperature and low pressure conditions. So we tend to find a lot of slate really closer to the surface of the earth than what we find in the next example. In the next example, we have the igneous rock diorite. So remember, the diorite is an igneous rock that formed intrusively from plutonic forces or processes. We've got a pool of magma that slowly crystallizes and cools over time to form this rock. So we've got diorite, and diorite, if you add a lot of pressure, a lot of heat to it, what we call high grade conditions, it can metamorphose into gneiss. So That is, again, high grade. So high temperature, high pressure. And of course, there's grades all in between. And again, there's different sequences of metamorphism that can occur as well. So these are just some examples out of many that show this process of gradation, again, differences in heat and pressure over time. So I'm going to show you some of these transitions on this slide. We've got the sequence of metamorphism that occurs as we continue to add heat and pressure to shale. So shale's our starting point. Okay, that's our sedimentary rock. And there's a lot of variability, remember, in the Earth's crust. So if we continue to add heat and pressure to it, let's say we take shale, you add a little bit of heat, add a little bit of pressure, it will deform into the rock that we call slate. If you continue to add heat and pressure to slate, so again, shale to slate, low-grade metamorphism. Continue to add heat and pressure to slate, slate will again metamorphose into phyllite. Continue to add heat and pressure to phyllite, it will metamorphose into schist. And if you continue to add heat and pressure to schist, it will metamorphose into gneiss. Now, gneiss is the last rock in the entire sequence, which means that at this point, it's the highest grade. So you get the most heat, the most pressure here. If you were to continue to add heat and pressure to gneiss, it will just melt down. It will melt back into magma solution. So it will melt back into magma solution, and then that will be that. So if we were to think about it in terms of, well, what's our parent rock? The parent rock of all of these rocks in the sequence is shale. But understand that because metamorphic rocks can form from not only igneous or sedimentary rocks, but also from other metamorphic rocks, if we were to look at something like gneiss, the parent rocks of gneiss in sequence would be shale, slate, phyllite, and schist. So gneiss has multiple parent rocks in this sequence. Shale, though, is the main parent rock for all of these. So again, the only parent rock of slate, for example, would be shale, but the parent rocks of gneiss would be shale, slate, phyllite, and schist. Finally, on this slide, we've got some more examples of the transitions between parent rocks and common metamorphic rocks that we encounter in nature, and in particular here in California. So let's take a look at this. We've got sandstone, which metamorphoses to form quartzite, as we've seen. But then we have the rock basalt. Basalt, remember, is an extrusive igneous rock. It generally forms on the seafloor. And basalt is something very interesting. So it develops on the seafloor. Now, which of these rocks, you think, formed due to regional metamorphism? Well, as it turns out, the one that formed due to regional metamorphism is serpentine, or serpentinite, which is shown here. So serpentine is the metamorphosed form of basalt. What happened was that starting around a few 100 million years ago till about 25 million years ago or so along our coastline in California, basalt on the seafloor that was connected to the Pacific Ocean, that was connected to the Pacific Plate, became subducted. It became pulled underneath the continental plate of North America. And in that process of subduction, basalt became metamorphosed into serpentine. And so that's why serpentine is our state rock. Serpentine is our rock because it shows evidence of this process of subduction. I'll tell you more about the geology of California and how the surface of our landscape has been completely changed through metamorphic processes and other processes in a later lecture. Again, we've got quartz sandstone at the top. So serpentine formed due to regional metamorphism. Thus, serpentine is considered a foliated metamorphic rock, whereas quartzite, as we can see, formed from sandstone. That particular specimen formed from non-foliated processes from contact metamorphism. And we have both of these metamorphic rocks in abundance here in California. So remember that quartzite forms from the recrystallization process, the addition of heat to sandstone, contact metamorphism. Serpentine formed from that regional process. We've got the subduction of that basalt from the seafloor, against the North American continent, and that is what generated that rock over millions of years. So this officially ends our tour of the rock cycle, and next week we're going to begin learning more about different types of geologic environments. We're going to start off with an investigation of groundwater and how that can develop and alter the topography of Earth's surface. So thank you for watching, and I hope to catch you in the next lecture.